For the faculty members especially, we have actually asked Mr. Amit Seni to get benefited our faculty members, especially from what VLSI and circuits and systems related tools we have. So yes, it will be very useful session for all of you. Thank you.
Thank you, ma'am, for introducing me. Good morning to all of you. Myself, Amit from CAD Design Systems. And basically, first of all, before giving you a demonstration, I will give you a brief introduction about our company and the products that we are using. So we are having multiple TCAD products based on their applications. So what we are doing basically, first of all, I will tell you about us. We are basically around 15-year-old company, and we are basically dealing into semiconductor device modeling softwares, EDA tools, and spice modeling services. We are also providing radiation hardened silicon proven IPs. So we are having a TCAD tool mainly for semiconductor device and process simulation. We are having simulation software for perovskite and organic devices, mainly for OLEDs and organic photovoltaic cells. We are also providing spice modeling services and fabrication related services. We are also providing equipments for OLED and OPV measurements, silicon proven IPs, mainly radiation hardened IP like radiation hardened memory compilers and analog IPs, interface IPs. And we are also doing PDK development mainly for radiation hardened logic. So RS PDK library development and a PDK development we can say. Along with that, we are also providing professional training mainly to TCAT, to the industry and to academia, both. So the products that we are having a classical TCAT tool, we are having a nano device simulator, we are having a NEGF simulator, mainly for 2D materials. So three type of TCAT tool we are having. Then we are having a tool for organic devices and a custom IC design. So for classical TCAT tool, we are having a tool set that name is Visual TCAT. In Visual TCAD, we are having multiple modules, like we are having a simulation manager, we are having a 2D, 3D device simulation software, we are having a 2D, 3D process simulation software, a workbench, a RCX extraction, a spice modeling, and a structure editor. So the modules are like this: Visual TCAD simulation manager. Now, previously the device simulator name was Genius, but now in the latest version, 2024 and onwards version, we have modified the device simulator. Now the version name is C device. This device simulator name is C device. It is now 2D, 3D device simulator. Now we are also having a process simulator that name is C process. We are having a workbench environment that we call CWB. We are having a R6 extraction that we call CRCX, and a spice model extraction tool that we call TCAT2 spice. Then for visualization, C visual. For 3D CAD designing, we are having C structure. So these are the modules we are having under Visual TCAD environment. Visual TCAD environment also supports radiation hardened module. For radiation hardened module, we are having a separate tool set that we call radiation hardened module. Using that, you are able to do single event effect and TID simulations on your devices, single devices, as well as on your small circuits also, like SRAM cell, or maybe a storage cell for a D flip flop, or maybe any register. So you can make your storage device will be a radiation hardened storage device. For 3D, we can say emulation purpose, we are having a module that name is GDF2 mesh. This GDF2 mesh module is used to model a 3D structure of any single device as well as a circuit. Now, recently we have also introduced one more module that name is Visual TCAD 3D emulator, and in that emulator we have given an interface of basically a 3D. We have given an interface with a 3D printer. I will show you the image. Image will be like this is a 3D image, like emulator image, and we can also print it. We have done a printing. I will that image I'm showing you. Show you the image. I hope this image is visible. This is a process emulator. We have done our printing through a 3D printer. So the main aim of this is nowadays 3D vertical ICs we are able to print through a 3D printer. So we can also model, and we can do the zoom x of this device by 1,000 times or maybe 10,000 times, and then we can print through a 3D printer to check the topic profile into 3D. Okay. This is all about the classical ticket tool. Then we are having a nano device simulator. This nano device simulator is basically from a company Global Ticket. It is a European ticket tool. So it will be mainly useful for novel architecture and novel devices, like mainly for technology targeting to 14 nanometer and lower till 1 nanometer. So here the device simulator name is Nano Device Simulator. It also comes with all the modules like device builder, simulator, workbench, and here the advantage is it supports advanced scattering related simulations, and also support a mono layer of 2D materials. Like if someone want to use a mono layer along with the silicon devices like MOS 2 layer or something like CNT based interface, then that kind of advanced simulations you are also able to do in global ticket environment, whereas those things are not possible currently into visual ticket. Go visual ticket is a classical ticket tool. Here you can work till 5 nanometer, and beyond that if you want to work, you are able to work using a nano device simulator. Nano device simulator is mainly for microelectronics devices and novel architectures. Then we are having a NEGF simulator, that name is Q star simulator. This Q star simulator will be mainly useful for graphene and carbon nanotube and other 2D materials. It also supports a heterostructure using graphene and 2D material, or using two different type of 2D materials. So if you want to make a heterostructure where you want to use both 2D materials, graphene or CNT, like interface of graphene with any other 2D material, that kind of structure it also able to simulate. So this is purely a NAGF simulator. Then for organic devices, we are having a simulation software that name is SetPOS. It will be useful for OLEDs and for organic photovoltaic simulations. For custom IC design, we are having an environment that name is Simica. This is an AMS toolkit. It will be very much similar to the Cadence Virtuoso environment. So all like look, feel, shortcuts, everything it supports from the Cadence. Whatever, even the PDK, the same PDK you are able to import here. It is able to import OA and skill-based PDK. It is able to export OA, skill-based, and their proprietary like format these PDKs. So you are able to import here. Also OA and skill format you are also able to export here. So this is one of the product category we are having. Then for optical proximity correction, we are having a different category. This will be mainly useful for mask preparation. This product is mainly for the fabs, so where they can do the lithography simulation and they can produce mask. Then, as I told you, we are into radiation hardened PDK development. So we are also providing services. We are having like PDKs mainly for 180 nanometer, 130 nanometer, 90 nanometer, and 45 till 45 nanometer. 32 nanometer technology development is under process, mainly into radiation hardened. So when we talk about radiation hardened, So our all standard cells are radiation hardened. That will be useful for space grade, basically, or we can say a universe grade electronics you can easily make. Where the tolerance will be PID tolerance is more than 300 kilorad, SCL tolerance will be more than 90 MeV. So this is the tolerance level. That, and all this all this library we verified through our TCAD physical simulation and through experiment. On service side, we are providing consultation and services into device modeling, radiation hardened consultation, and fabrication. We are also running a training course for the academics, in which we are providing 2 weeks to 24 weeks advanced training courses, mainly to device simulation, process and device simulation category. If some of your students want to will be interested in the TCAD courses, they can apply to our website. They get the more detail from there. Now in the visual TCAD, we are having a process simulator, we are having device simulator, and we are having interconnect simulator, mainly for RCX. So in this session, I will give you a brief demonstration about the visual TCAD tool. This is the products come under visual TCAD. Now I'm giving you a live demonstration. I'm closing my PPT. If any of you have any query till here, please ask me. Okay, I'm just opening the software. This software support basically Linux operating system. We support Red Hat 6, Red Hat 7, RHL 8, and Ubuntu environment. My screen is visible to you? A Linux screen is visible. Please confirm. Ma'am, please confirm my Linux screen is visible. To open this, hello, are you getting my voice, ma'am? Can someone confirm me either on a chat? Okay. So first of all, I will show you what are the modules you are having. We are having our modules here. Source the software. So we are having a module for structure editing or structure designing. We are having a module C structure. So this is a structure editor. Here we are free to design a device either into 2D or into 3D. Like if I take cylindrical, we set the coordinates, set the radius, and then okay, we fill it with the material from here, silicon, right? If you want to exclude the shape, reduce the shape or exclude dimension, we can use this. Like if you want to exclude it with 5, increase the size by 5 micron, like this. So we can make any shapes, like if you want to add this here, so any like silicon material here, you can easily make your structure here into 3D or into 2D. If you want to make a 2D structure, you can make a 2D structure also here. Now this is a basically a structure editor. Then we are having one more structure editor, that name is a 2D drawing tool. So in this drawing tool, you are only able to make your devices only into 2D. So here we are having uh, a polygon shapes. You can easily make any shape here, whatever the shape we want, and we can fill it with the material. Like if I can show you here, this is a double gate kind of structure we have drawn. This is a nano sheet in 2D we have drawn. The same structure we open into 3D. This is a 2D we have drawn in 2D and we have converted it into 3D. Now these are the two device editing tool we are having. Then here we can also write as scripts. You can also write a script here. First of all, I'm just showing you the modules that we are having. Then we are having here interface with the layout editor. This is the layout editor. So in this layout editor, what if we design any layout, like this is the layout. Like if, so we can easily fabricate this layout 3D structure. We can easily fabricate from this layout using a module GDS to mesh. So this is a tool where we can easily fabricate a 3D structure. In this, we give a layout as an input, a GDS file we provide here as an input, and it will give us a 3D structure as an output. So here we can edit the process parameters. Now we are also having a workbench here that we call CWB. A workbench. So in this workbench, we are able to do a simulation. Like here, if I show you a process simulation, a device simulation, like this is a process simulation for a diode. This is a process simulation for a MOSFET at 28 nanometer technology. So the coloring here, the coloring shows the different state. Like green color means it's finished. Pink color means aborted. The simulation was aborted. So how the device look like? The device look like, we'll open a visualizer. here the device. This is a device. From here we can select what type of profile we want to see. If we want to put a cut line, we can put a cut line. Then we can select what in this cut line what we want to see, boron profile or arsenic profile, whatever the profile we want to see, we can easily see the profile here. The meshing here. So this is basically our visualizer, and here the script we write here. If we open this, or if you open any option here, we write a CMD file. This is a process related CMD file. The CMD file, once it will run, the log file will come here, out log, and the output will be this output we have opened in a visualizer. This is a process. Then this is a device simulator. If I open, this is a device simulator script. Here we define the conditions. We give the input. We define the boundaries, global settings. Because if any stress model is enabled, this physics related to the stress will be passed. Then here we define the physics, PMI interface, then biasing. Here, just a biasing. So this is a workbench environment. Here we are controlling the models. Work function, finale model, filter model. This 1 means model is enabled, 0 means model is disabled. So if you see this one, see this. The Boolean expression 1 and 0 we have made so that we can enable or disable the models. This is basically a typical format of the script. Now this is a workbench environment. In workbench environment, we have integrated device process simulation, device simulation, and then a parameter extraction also. Here, once the simulation will be done, the plot result will be plot, and the parameter extraction will be comes like this. Threshold voltage at linear, threshold voltage at saturation, then the on current at linear, on current at saturation, off current, and slope. If further more you want, like once you have this data, you can easily extract other parameters. Or if you want to extract a complete spice model, so we are having an environment here to extract a complete spice model. So if you want to see that one, I will show you. This is a FinFET process example. In this, we have written a FinFET process script, then a FinFET device script. We are doing work function 4.4, linear at 50 millivolt, saturation voltage 0.8 volt. Then we are doing a ID VG simulation, lin and set. Then ID VD simulation at 3 different gate voltages, 0.4, 0.6 and 0.8. Then after this CV simulation, then we are doing a capacitance extraction, and here we are doing a model extraction, bin model. instruction. So if you see this one, command file, okay. To rerun this job, get this uh, reprocess. Okay. Currently this is okay. I will show you here. It will be okay. This one, the name was bin model. Bin model. Bin model. This is the abstraction script. This script is calling this one. Yes, this script is calling this. So this is a complete script to extract a spice model from a FinFET. Okay. So now these are the basic overview about the tool. Now I will give you a demonstration. We start the demonstration. First of all, we want to design a device. We open a TCAD software. We will draw a structure. So what structure you would like to see? A diode or a MOSFET or a double gate MOSFET? Can someone will tell over this chat message? To design a device, first of all, I open this Visual TCAD environment if we want to draw a structure. If you want to write a script, we can easily write a script also. Right? For writing a script, we have to use different method. We have to use a scripting method like if I can show you. Like this is a simple FinFET structure. So this FinFET structure we have designed using a script. I hope this scripting will be visible to you. So we define X mesh, Y mesh, Z mesh, a coordination, then the coordinates, then doping information, these things. Now if this is a scripting method, using that we can easily make this type of structures. 3D structure with mesh. Now I will show you our drawing method. Drawing method, we go file, new, device drawing, and here in this work environment we can easily draw a structure into 2D. So by default this grid size is 0.1 micron by 0.1 micron. So we can reduce this grid size as per our requirement. Now it is 0.01. Further if you want, now it is 0.001, 1 nanometer. So based on what type of device we want to design, accordingly we regrid this structure. So I will do it 0.01. Okay. Now I will delete this one, So grid size is 0.01. So what structure you would like to see? MOSFET or double gate MOSFET? Double gate MOSFET will be okay. Okay, let's we draw a MOSFET. So drawing a MOSFET. So we consider this as this is a plus point, is a center point. So if we want to design a MOSFET of, let's say, 45 nanometer, 45 nanometer will be, this is 10, 20, 30, 40. Okay. Uh, Everything here, 13 here, 13 here. Okay, this will be around 46, 26. Okay, 45 nanometer. No, we resize this work area. 22.5, 22 here, 22 here. Okay, now we take a rectangular box. Okay, we take a rectangular box of this size. The size will be, total sizes will be 0.1 micron. Okay, now here we make a structure. So what I will do, I will make a, okay, I will make a top contact structure. So top all contacts I will take from the top only. So what I will do, I will increase the size of this furthermore. Now instead of this, uh, X will be positive, X will be negative. So here I increase the size, 9, 9, 9. Okay, so this is the way I increase the size. Now what I will do, we'll make a contacts. So we consider this portion as a source contact. We consider this portion as a drain contact, and from here to here we consider as a gate contact. Source, gate, drain contact. Then we consider one more contact this side as a bulk contact, a body contact. Okay, now we take a to give the shape, we consider add arc here. This is the arc shape. Line. Okay, then here we consider a line. This contact is little bit down, so I make a uniform contact. Lift and a line. So my skeleton is currently ready. Now here we fill it with a different materials. So we have a add region label property here. Add region label. We define a body, name body. Material will be silicon. Here we are having a list of materials. Silicon. We are having multiple materials here. Conductor, insulator, okay. So we consider silicon having mesh. I will give 0.04. So our silicon will be filled in this box. So we consider it as a complete silicon substrate or a vapor. Then we put a contact here. I give a substrate contact, a metallic contact, aluminium, or we can say bulk contact, source contact, aluminium, drain contact, aluminium, then a gate contact and polysilicon. Okay. Now here we put a gate oxide. Considering the size of gate oxide is currently the size of the gate oxide is 1 nanometer. Gate oxide thickness is currently this size is 1 nanometer. If you want to increase this thickness, I just resize this box here. So the Y is my 1, so I will consider this as a 2. I will make gate oxide thickness 2 nanometer. So now it is 2 nanometer. I will shift 2 nanometer. So we fill it with the material GUX, give the label SiO2. Now the oxide is filled. Here you want to give a space. This is spacer. We want to give SiO2 or any other material. You may give any other material. That insulator material only, or maybe spacer 2, maybe air, or maybe nitride, or maybe anything you can give here. Now here spacer 3. If you see, currently the structure is like this. Now this silicon we have added is an intrinsic silicon. So now we make it, we add an impurity here. Okay, the gate length is, you see the gate length around 44 nanometer, or maybe it will come to 45 nanometer. 44, 45, it's okay. Now what we do for impurity, I just make it transparent first of all. Properties. Now it is transparent. Now we save this file first of all. I will save it on a desktop demo folder. I will create one folder. J here 45 MOS. This is a structure file. This structure file I have saved by this name. Now there is the option add doping profile. So initially our complete silicon is intrinsic type. So now we make it p type. So uniform doping, p type doping means acceptor. By default concentration likely dope 1 is 16. Okay. So the it is a p type substrate. Now above this we are having a body contact. So p type substrate body contact means we are having here a this will be a perfect contact. So for that purpose p plus acceptor I make it by 19, junction depth 25. Okay, so this will be act as a perfect body contact, ohmic contact. Now this region will act as a source. Ah, again Gaussian lightly doped source region. So it will be anti 5E18 I can say, junction depth 5 nanometer. Okay, Gaussian doping, source doping. This will be a deep implant 1E20, junction depth 25 nanometer, XY ratio 0.6. Okay, the same thing we do for drain region. Gaussian LDD for drain, donor type, same concentration whatever we have given, 5E18. Okay, and just here the direction we have to change. Now same again, drain doping 120, donor again 25, 0.6. Okay, so let's recheck whether the how the profile look like. We built a mesh. Okay, the profile is like this. So there is some issue in this profile, so we reconstruct this profile. Okay, fine. Okay. let's say built. Okay. Again, the dimension. We have to verify with the dimension. What is dimension? Okay, this total length is 80. Total length is okay. So we have to carefully add this. That is 80. Fine. This looks better. Now further we verify or further tuned it. Okay. Okay. Now we built. Fine. Fine. It looks better. Furthermore, we tune the profile. Okay. Now, now the profile is like this. Source and drain profile. This is a substrate. This is a top contact substrate. So we built a mesh. The profiles are like this. Now we refine the mesh. So once we do refine mesh, it will refine the mesh two, 3 times. 2, 3. Now what it is doing, it will refine the mesh from the PN junction. Okay. Now how the device will look like? Device will look like this is the device. is the body contact on the top. From the top, we are also free to take body contact from the bottom, but we are taking top body contact, source contact, drain contact, gate contact. Now we save this file, save mesh2 file. We give the name 45 MOS. Then we open it. This is the doping profile we are having. Acceptor, donor, and doping. Currently it is showing. If we do this, it will be more clear. Okay, total doping profile are this. Meshing will be this. We can put a cut line, and we can also plot a profile curves. Till here, any query? If someone have any query, please feel free ask me. If anyone of you have any query, now we convert this device into 3D.
Hello.
Yes, ma'am.
Mr. Seni, if we can take a 5 minutes break, maybe you can have a glass of water or maybe
Okay, okay.
after that 5 minutes break, let us have. And by the
Okay.
time if you have any query, dear participants, you may type in the chat box.
Yeah,
The
we will
device
type in
is
the
most of device we have discussed already. So whatever cut he is going to tell, sir, show them vertical cut and horizontal cut for the EB diagrams. We have already discussed theoretically yesterday, so
Okay.
that they can understand, they can visualize, because it will be the hands-on session for whatever they have learned from the energy band diagrams, how the
Okay.
things are
Okay.
going to
Energy
happen.
band diagram, ma'am, after simulation, I will plot energy because
Yes, yes.
energy band diagram will come after simulation, but the doping
So,
profile curve I will show after this break. I will show the doping profiles.
yeah, so I request you to tell them both.
Hello, voice. Hello, hello. I'm not getting your voice.
Yes, I'm so sorry. It was not audible. I actually muted my mic by mistake. I have muted my mic. So I was just requesting, just show them the horizontal cut and vertical cut, sir. For example, the cut through this vertical line, I have requested for the presentation control, if you can permit for 1 minute. Yeah. So this vertical cut and then horizontal cut, a doping line, energy band diagrams and everything, electric field, how it is looking like. So in the saturation, whenever device is there, so they will be able to visualize the pinch of. Uh,
I will show them everything to them. I will show
yeah.
energy band diagram, how the channel is forming, how why we call it field effect transistor, how the electric field is growing in the gate oxide region. Everything I will show
Okay, sir.
after
Take
simulation.
a
Okay.
5 minutes break and let us meet back at 12:10, sir. Thank you,
Okay.
sir.
Okay. Thank you. Thank you.
So, dear audience, let's back at 12:10.
Shall we start?
Yes, sir. Please start.
Okay. I will share the screen once again. Ma'am, you have to make me presenter.
No, no, you share the screen and then start, please.
Ma'am, actually it's showing only meeting organizer and presenter can share. So you
Let
have to
me
make.
check.
I think I am not
Okay.
a presenter now.
Dr. Geeta,
Uh,
are you there?
yes, ma'am, I'll make it.
Yeah, please make him presenter. So sometimes internet connection actually get lost. Now you are presenter, sir. Please.
Yeah, okay. My screen is visible.
Yeah, it's visible, sir. Please carry on.
Okay. So in this structure, I've make a I've not taking much thickness. I'm taking only 80 nanometer thickness. So that's why it's look like this. But if we want to see we want to plot the doping profiles. So the contours we are able to see from this option: net doping, acceptor, donor. Okay. So all type of profiles we are able to see. Currently, they are showing into sine log scale. Linear scale we get like this. We get the accurate depth here. Similarly, linear scale, the depth will be this. So if we make a plot of this, so if you want to see the plot, we select cut line option here, net doping, not this is donor doping profile. So donor doping profile, vertical cut line we put. So this is a vertical cut line of a donor doping profile. Okay. Now we want to make it more attractive, we make it more attractive, more thicker. Then the plot properties, like currently this is the sine log scale. Previously it was a linear this is scale. Logarithmic scale, you can change the scale also from here. Now this is a way vertical doping profile. Horizontally, if you want to see net doping, because here we are having the acceptor doping also. So we want to take a cut line and we put a horizontal cut line. Once you do the horizontal cut line, we are able to see the doping profiles. See, in the channel region there is no doping. The concentration is 1:16. See, this will be much more in here, and want to make it more thicker. With the bullets. So if you see, here the concentration is very much lower. Here we are having source and drain concentration. Currently this is basically net doping, acceptor doping here. If you see, acceptor doping only this side, body contact side, donor doping here, net doping, total doping concentration, total doping concentration, the doping concentration of our body contact also. So this way we can check the doping profiles. Now this doping only before simulation we are able to check the doping profile. Now after simulation we are able to check everything. So now what we do, we convert this device into 3D first of all. For 3D conversion, we write a script. Yes. Save this script in the same folder. That is J. and I will increase the font size so that it will be visible to all of you. This is the script. So here my file name was, we give the import the file name was 45 mos.tif. How much jet width we want? Let's suppose we want a jet width of 0.1 micron, 100 nanometer, and let's suppose 10 spacing, 3D 45 mos. This will be the output. So here we are importing the file, adding jet dimension in it. Then once we add jet dimension also requires some grid. So 10 grid lines we require in that extension. Then we're saving the file into. So we have this small script. We save this script. Now after this, if we want to run it, we run it. First of all, we move to the folder MNIT. The folder name was not here. Okay, in the demo folder. ITJ. So here we have a file. This file. So first of all, I will source the software. Now here I will write C device. This is a batch mode way to work on simulator. C device -I input file name is aa.inp. This is the input file aa.inp. We run it. Just enter. It runs. Read the file and extend jet dimension. After jet dimension extension, this file is done in 9 seconds. Just in 9 seconds, it consumes this much MB of like 2 GB RAM memory, and it saves the file in just 9 seconds, 9.5 seconds. Now we open this file. This is the file. So we have designed into 2D and we have converted it into 3D. You see the grid lines. First of all, the jet grid lines. See, this is the mesh, and jet dimension we give 10 grid lines. So if you see, these are 10 equal sections we make. Now, want to see the doping profile into 3D. You are able to see 3D doping profiles. Holes. This is the acceptor doping profile. If we remove the contact, polysilicon, nitride, oxide, only silicon. This is the only silicon. Now want to see the electrons. Doping with logarithmic contour if you want to see pseudo property. The logarithmic profile. Here we can change heat mode or different color modes we can change here. There are different color modes. Okay. Now add oxide, then nitride and contacts polysilicon. This is the one method. Another method we want to see the point. The point method, representation through wire, representation through surface with edges. So there are multiple ways to visualize this. Now our device we have designed in 2D, we have converted it into a 3D. Till here, any query? If you have any query, please feel free ask me. Now we will simulate this one. For simulation, there are two methods. Either we can write a script here, or we can write a script in workbench environment, or we can do a GUI based simulation. So in all the way we can do this. So if we want to do this through a GUI method, so I will do this. We open TCAT. Here I will load the device, 2D device, to demo folder. ITJ 45 this. Connected, running. Console, we can hide the console like from here. And now the device get loaded. So this device having 4 electrodes: substrate contact, source contact, drain and gate. So what type of simulation? DC, AC, transient circuit element. So accordingly we may do the simulation. So first of all DC. Now here gate contact, work function, whatever, let's suppose you want to set a work function 4.6. This is the work function. We may select. If we want to short 2 electrodes, we can short 2 electrodes using interconnect method, like substrate and source we short, and we give the name as con. Then okay. Now we are able to see here only 3 contacts. As contact means our gate, our source electrode and substrate are interconnected. We give the common terminal name. Now we run it 50 millivolt. Voltage shift from 0 to 1.2 volt in a step of 0.05 volt. We save this file. MOSFET. If you want to enable models here, we click on here the model profiles. Like for silicon, we want to enable permidirect. Tunneling model, if you want to enable, we can enable tunneling if you want. Or high field mobility, we make it disable. Mobility model, I will just make it enable to Lombardi model. Okay. So basic set of model I just enable. Now I save this file. Then to run, I will click here run. We run it in a separate folder, run folder. So now the file is in progress. See, the simulation is running here in setup window, and in result window the simulation is running. See, first it will ramp drain to 50 millivolt, then it will start ramping gate to 1.22 volt in step of 50 millivolt. Currently the simulation is running. So once the simulation will be over, I will open the results. So now the simulation is completed till here. We select all this results, right click, open spreadsheet. So once we do this, we are able to see the current profile of each and every electrode available. So now we select I drain and gate. We apply gate voltage. We plot this, so we get the IV characteristics of our device. Now currently in this structure, the leakage current is too much high. Reason? Because we haven't add a threshold voltage implant. If you see the same thing in the device, right click, open visualization, the leakage current will be too high in our device. logarithmic, we enabled log plot. If you see, the leakage current is, there is a leakage current. Due to this, if you see this, we are getting the leakage current of the order of 5 because there is no threshold voltage implant layer. We haven't added a threshold voltage or a channel stop implant layer in our device. Because of this intention, because there was a region that if we don't put a threshold voltage implant or a channel stop implant layer, the leakage current will be very high. So now I will change the structure and I will add that layer. I will open this file. We haven't saved the doping profile file. Okay. I will make a redoping in this structure. For you, it will be a revision. I haven't saved that file now. That's the reason the doping profile are not saved. Uniform doping 2015. P-type. Body contact. Gaussian. PP. Acceptor 1E19. 0.5. Then this will be source doping. Lightly doped source region, donor type 1E18, nanometer 0.5, source doping, donor type 1E20, 3 nanometer 0.4. Same thing for drain. LDD for drain, donor, and 5. Drain doping 20, 15 nanometer 4, and here I will add a channel stop implant. Gaussian VTH implant, it will be acceptor type 1E18. So this will be a channel stop implant layer. So this channel will stop implant will help. Here what we are doing, we are increasing the concentration of holes so that the free electron will not move so in the channel without any built-in potential. Like with MOSFET having a built-in potential, so that potential is very much sufficient to flow the free carriers. So to stop them, we have to increase this. Now we make a mesh. Something is still wrong. We have to do remodeling. Drain. This will be 0.2. This will be 0.2. Yes, now it is okay. Now we do the mesh 2-3 times. After this, we save this file. We save the output of this. Yes, overwrite. Save this file. Now we load this file again here. And rerun this job. 50 millivolt and get to 1.2 volt in step of 0.05 with the same biasing condition. 2.6 was the work function, and here the same model. Direct, high field disabled.
नहीं मैंने 1 से 5 शेड्यूल कर रखी है, पर मैंने 2 बैच है। मैं कल करवा लेती हूँ दोनों बैच, फिर आप फ्री हो जाएंगे, आप करवा लेना बचे हुए 3 बैच। एक्चुअली मैं एफटीपी करवा रही हूँ ना सर, फिर मैं 2 टाइम नहीं उनको मंडे का
still be visible. I have okay. Just save this file once again and run it. Run again in the run folder. So now you will be able to see the difference. These are our old results. So I just make it comment it old. So the old results. Now the new results will come. So you are able to see the difference. Okay, now plot spreadsheet. Now the same I will add here the old results along with old results. Insert curve. X variable will be gate voltage. Y variable will be drain current. Add. So we are able to see the difference in both the results. Now the same thing, if you want to see here, spreadsheet, electron density, this into 3D. Now we see here, once we are increasing, the channel start forming. The channel start forming here. As the gate voltage increasing, the channel start forming. Since the VT is low, drain voltage is low. Now the electric field. So if you see, this is the electric field at high. Initially there is no electric field. This is the no electric field because we call it field effect transistor. So electric field will be visible in the oxide region. So once we click here, we are able to see in the gate oxide region. Field will be visible like this. Once the current will be saturated, field will be settled down. Now this is the contour profile. All this profile we are also able to see. If I want to see, I will show you through a cut line frame lift. Here we are having result 1 to result 1 means when the gate voltage is 0, and result 25 means when gate voltage is 1.2 volt. So I will do the comparison for both of you, for both of the results. We do the this plot open. Now here we add result 1 and result 25, both file we open. Now I want to see the electric field in both the files. You are able to see the difference in the electric field. Here the electric field is low, here the electric field is high. To see. Here the contour you are able to see from this plot also, from this, see the 7.6 and here the value is 4.45. The difference, the electric field is high. If you want to plot or the here the channel formation, here the channel formation is low, there is no channel formation. If you want to plot electric field, if you want to plot, we just overlap both the files, control A, cut line in the oxide region, put a cut line. Now we are able to see the difference in the electric field. Green one wins when there is no two. When the gate voltage is not applied, the green one, electric field profile. When the gate voltage is applied, the red one, the electric field profile. Now want to see the channel profile. Again overlap the channel electron, control A, plot here on the surface, silicon surface. See, there is no channel exist. There is a channel is uniformly exist. The green line here, the 25 means green line. Region 25, I will increase this legend also. Okay, visible? Is it visible? Please confirm it is visible.
Yes, sir, it is visible.
Okay. Yes. Now, similarly, now I will plot a conduction band and valence band profiles. So these are channel. Green one is a channel formation. There is no channel. Red one, no channel. The electron concentration is lower. Now, for conduction band and valence band, we again overlap both the structures. Then we select here EC, EV, both. Fermi level, if you also want quasi Fermi level, you can add quasi Fermi level also. Now, if you make a plot, Let's suppose in the channel region we make a plot. We make a plot here. Not this one. This one is, we have to make a plot, vertical plots. So this is the conduction and management profile. So overlap, we take a vertical profile. MOS profile. MOS will be gate oxide semiconductor in the channel region. Yes, this is the profile. Initially this, so the Fermi level is aligned here. So EC is this, EV is this. So what I will do, I will remove this. If you see this portion, make it little bit darker. Two. Initially, the conduction band, this red one is a conduction band profile. When there is gate voltage, there is no gate voltage applied. The gate voltage is 0. And when the gate voltage 1.2, it is bent towards the Fermi level. This one is a Fermi level. So the band bending we are able to see in the semiconductor region. In gate oxide region, the bands are different, and in the oxide in this metal region, these are overlapped. The bands are overlapped. Gate region, bands are overlapped. Oxide region, wide band gap, and in the semiconductor region, without applying biasing, this red line, and after applying biasing, we are able to see the band bending towards the Fermi level side. Is it clear? Any query till here? Similarly, if you want to plot mobility, this is the mobility profile, electron mobility, hole mobility profile, recombination, SRH recombination profiles, Auger recombination profiles, all these profiles you are able to see. Okay. Now, the same thing you are also able to visualize through a contour. This is a contour. Want to see the potential? The potential profile. This is the electric field profile, electron profiles, holes profile, Na, Nd, doping concentration, net charge. Then there is SRH recombination profile, Auger recombination profile, mobility profiles, hole mobility profile, conduction band profile, valence band profile. All these profile, then the temperature is we haven't enabled. Then this is the flow lines, the current flow lines, current flow line profile, electric field. Now, if you see this total current or electric field profiles, we can also see here the junctions, flow lines. You can see the flow lines here and a profile like this. If you want to make a cut line, you can take cut line of all these things. Or if you want to make a probing, so probing, we have a probe option. Put a probe anywhere, all the profile you will get to particular location. What are the value here? You can easily get the probe option. In that way, you can do the inner engineering of your device. And if you want to export this, you can do the single image or a work. Single image means either any of the single image, or export work area image means both the image get simultaneously get exported. Like if I will export, so if you see here, both the images, this complete image we get. This is the export option. Now data manager, we also get the data. Whatever the cut line we are having, accordingly we also have a data for all the cut lines. Whatever the cut line we have added here. So whatever the data we want to export, we can easily export into a DAT format or raw format that you can easily open in Origin or in Excel software. Now once this simulation will be over, currently once the simulation will be over, if you want to do a mixed mode simulation, then you have to convert this device. If you want to do AC simulation, you can change the simulation mode to AC, and here you want to apply frequency, multi-frequency or single frequency, you can apply the frequency source to the which electrode. Let's suppose gate electrode, you will get the AC simulations. If you want to do transient simulation, you want to apply a pulse source or a sine wave source, you can do the transient simulation. If you want to make a circuit simulation, go to this, convert your device in form of symbol. Like I will change the symbol to a numerical symbol. I will lock this pins, pin S with source, pin G with gate, pin D with drain, pin B with the substrate contact or body contact. Now we save this file, MOSFET. Now we call this MOSFET sim file here. And we can make a circuit simulation here. Like if I want to do, I can take any other element from the library. Let's suppose PMOS 180 I will take along with this. Might be the results will not come correct, but I will try to produce an inverter for you. I will make an inverter circuit, just do a interconnection. Here the difference, this blue color is basically a device having support SPICE model. Length and width I will define here. This black color is a TCAD component. This is a SPICE component, this is a TCAD component. Now we add a voltage sources. Let's suppose pulse and a DC. Complete the connection. Ground. Now whatever the interconnect we have done, body with the source, grounded, okay. Now we apply 1 volt, let's suppose here, and we apply the probe, the output probe. We connect the probe here and here, ground. Now we do the simulation for pulse of 4 nanosecond. Total pulse will be 10 nanosecond, 0 to 1 volt, okay. The simulation analysis. Netlist floating component found. Floating component, okay, the gate electrode is not connected. So this body contact for this will be connected. Now again check netlist. Hanging node for only one edge. Some hanging node is still available. Okay. One edge connection to it means netlist. Let me save this file first. CMOS. Okay. Okay, this one. Now the netlist will be okay. Now we see, check netlist, okay. We save this file, save as CMOS. Now we done the transient simulation for nanoseconds. We change the time to nanoseconds. Stop time of 20 nanoseconds. Step time 0.25 nanosecond. Maximum 1 nanosecond. Okay, use initial conditions. Okay. Okay, we save this file once again and now run it in the run folder. So once now the simulation will start. Something happens here. Now we run again. Run 2 folder. So there is something wrong in this simulation. Let me find out what is wrong in this simulation. In the run 2, there was a log file. Okay. Let me run here. Simulation started. It's automatically making the VTU files in the background. Now, during runtime, if you want to open the results, you click here, open result.dat. By default, file name was result.dat. Here, the input is V1, output will be prop1. So we select time, because we are doing transient simulation. prop 1, V1. This is the red one is the input. This is the output. The why this is the output is lower because our devices are not for the same technology. We are using NMOS of 45 nanometer, PMOS 180 nanometer, different technology devices we are taking. So that's the reason. But we are getting the upward inverted curves. Still here, any query? Please let me know if you have any query.
So if there is any query, please let us know. You may type in the chat box so that we can take the query. No query? Okay.
I hope you are able to understand the flow of Visual TCAD. This is a basic 2D flow. Now for advanced simulations, we can work on either on scripts or on workbench. Like I will show you one of the example here. Like this is one of the DRAM example. In this DRAM, we write a script like this, and if I will open, you have to rerun it. The device was this. This was the device. This was the structure. This was basically our DRAM with the Sonos. There is a nitride here. Sonos in 3D. Ready? The 2D example, I will show you the 2D we have done. This was the Sonos structure in 2D. Same we have developed in for FinFET. So if you see, this is the nitride layer. So control gate, floating gate, DRAM structure. So the same thing we have done for a 3D structure. Now nanowire, nanosheet, FinFET, all type of structures you can easily simulate here. We can have, like I will show you here.
Sir,
Yes, ma'am.
time it may take, sir.
Okay. Just a minute, ma'am. This is the way we do the cell simulation. The inverter, complete inverter cell. This is the complete inverter cell we have designed using, if I remove the interconnects, this is the PMOS, and top one is a PMOS, this one is a NMOS. The length of the PMOS is, width of the PMOS is higher and width of the NMOS is lower. This is complete cell simulation. It's not only single device, we can also make here a cells also, like inverter cell or maybe any other cell like SRAM cell. You can easily design SRAM cell also. If I can open SRAM cell, SRAM. This is the SRAM cell structure. some item location. This is the structure. Yeah. This is the SRAM cell done for the commercial customer. I remove the substrate also. Add a substrate. So this is the complete with the interconnects. I will remove the interconnects. See the SRAM cell having 6 transistors. This is one inverter. This is another inverter, one pass transistor, another pass transistor. And these are the body contacts. Right? So here you are free to design single device. You are free to design standard cells also using CMOS technology, using FinFET technology, anything. This is one of the commercial structure SRAM simulation. There's a because we have taken a part of array of SRAM cell. So in this one cell is here, one cell will become on the top of this, on the bottom of this, left hand side, right hand side. So we take a array. So this is all about the overview of a visual ticket. If any of you have any query, please feel free asking. My contact details I'm placing here. The contact details.
Yes, sir. If possible, please share this PPT so that our audience can reach out to your emails.
I will mail you. I will mail you this PPT.
Yes, sir. Thank you so much, sir.
Thank
So,
you.
if anybody is having any query regarding to this or how the software can be purchased or all things, so this PPT we will be sharing with you. You may get in touch with Mr. Amit Saini. He is very helpful and he will